Our second lecture objective is to define homeostasis and explain its significance to the function of the body. Alrighty, so homeostasis is a very important concept. And the prompt question that we'll start with in order to better describe homeostasis is shown here. So how does your body manage to keep your body temperature, your blood pH, your blood volume relatively constant day after day after day after day after day after day, infinitely since you were born? How does your body do that? Okay, and that's the kind of question that you should have in your mind in order for us to begin describing homeostasis, because your body's doing all of these things. It's keeping all of these variables relatively constant. Your body temperature, right? This is why we have our sort of basal body temperature, because that number is pretty consistent. There can be mild fluctuations depending on the environment that you expose yourself to, but your body is going to strive to keep that at a constant number. Same thing with your blood pH, and the blood pH determines how much acid or base is in your blood. And again, the body likes to keep that variable pretty consistent. So how does it do that? Let's talk about the mechanisms by which homeostasis is brought about. So homeostasis is the ability to maintain a relatively constant internal environment, even in the face of external changes. So if I go out into the cold, and I know Duluth gets pretty cold, so if I go out into the cold with maybe just a t-shirt on, no, my body's not going to stay at its basal internal temperature. It's going to get a little bit colder, but it's going to strive. It's going to institute various mechanisms, whether that be shivering, in order to get my basal temperature back to that resting point. So even in the face of external changes, which can sometimes throw off those variables, homeostasis is the ability of the body to bring that back to that set point. And so the components of the internal environment that are regulated are going to be variables such as our body temperature, our blood volume, our blood composition, right? How much sodium, potassium, and so forth are in our various fluid compartments, and then our blood pH, how much acid and base are in our blood that would determine the shift in the pH. So these are some of the variables. There are many other variables that we can think about, our heart rate, blood pressure, many other variables, but essentially those are kept the same because of the systems of homeostasis. Now, this is going to require organ systems integration. And what this means is that there are many different players: the heart, the brain, the blood vessels, all of these various body systems working together in order to reset these variables. An example that I'll give is with blood pressure. So if my blood pressure gets elevated, let's say I'm stressed, maybe there's an exam or some type of life factor, and my blood pressure goes up, my body's going to try to get it back down to my normal resting blood pressure. And so my blood vessels are going to play a role in that. My heart is going to play a role in that. My brain is going to play a role in that. And that is what systems integration means. Another thing we want to bear in mind is that any disruption to homeostasis is the initial basis for disease and death. So when we think about disease processes, kidney disease, heart disease, chronic high blood pressure or hypertension, these various disease means that homeostasis has been permanently altered. So whereas my body likes to keep blood pressure constant, if for ongoing periods of time, extended periods of time, my blood pressure is chronically elevated, there's going to be a new set point that the body's going to try to maintain, and that is going to be the basis for disease. And what does that disease look like? Well, damage to blood vessels. If your blood pressure is now constantly elevated, it's more stress on the blood vessels of your brain, which can lead to a stroke, or of your heart, which can lead to a heart attack. So whenever we disrupt or throw homeostasis off, it's the initial step for disease and then death. All right. And I like to use this image here really to hone in on some of the nuance of homeostasis. So homeostasis is not the image on the left, neither is it the image on the right. Homeostasis is really the center image. It's the bringing back to the set point. So it's not to say that we're always going to have these variables at their perfect set point number, nor is it to say that those variables are going to be thrown off either. But it is the striving to keep them centered, it's the striving to bring those back to set point that really underscores what homeostasis means. Alrighty. Let's look at an example here. So when we think about a regulated variable, we're going to use this example of a car going up a hill to illustrate how our variables can change and what components are existing in order to bring about homeostasis. So the regulated variable is going to be the aspect that we're trying to maintain. And in the example we're using here, it's going to be the speed of our car. The set point is the expected value of that regulated variable. And the example we're using here, it's going to be, we want to keep our speed at 60 miles per hour. So our regulated variable speed, our set point, 60 miles per hour. So our car begins at the foot of the hill and we dial in that set point. As it tries to ascend the hill, because of the elevation, the speed naturally decreases, and we're now down to 55 miles per hour. And that is going to send off what's called an error signal. The error signal means, hold up, wait a minute, we're deviating from the desired set point. And so that error signal is going to go off when we get to 55 miles per hour. That is also going to trigger a mechanism to correct the set point variable. So what happens in this example is there's going to be increased gas flow to the engine. And that is going to aim to correct the set point. So we can see the speed begins to increase, which is going from 55 to 58 miles per hour. As the speed increases, as we get back closer to our set point, the error signal should get smaller and smaller and smaller until the error signal is turned off, because we're now back to our desired variable, our desired set point for the variable. And so when we get to the top of the hill, we're now back to 60 miles per hour. We're now back to set point, and the error signal is turned off. And this is how homeostasis is brought about, okay? So it is not that we're always at 60 miles per hour, and it is not that we're maintaining 55 either. It's that as soon as we deviate from 60 miles per hour, automatic signals go off, the error signal, mechanisms are set in place, the increase of gas to the engine that are aiming or striving to bring us back to 60 miles per hour. Now, in that example, we can think about negative feedback. And negative feedback is the ability to change our variable in the opposite direction. It is going to be a self-correcting mechanism that brings us back to the desired set point. So in the example with the car, the negative feedback is the idea that when we deviate from 60 miles per hour, there's more gas flow to the engine, which is going to shift our speed in the opposite direction. If the speed is decreasing, we want to have a mechanism that increases the speed so it brings us back to the desired set point. So this is going to be a self-correcting mechanism to turn off the error signal and reset our regulated variable. The error signal is going to be the difference where we are from set point to where we are currently. So the difference, the degree of the difference between our deviation from the set point and where we would like to be, our desired set point, is going to be the degree of the error signal. So if we're really far, let's say the speed went all the way down to 50 miles per hour, we would have an even larger error signal in order to self-correct that variable. Okay. Here is another example of what homeostasis in action looks like. And this one is regarding our blood glucose levels. So our blood glucose is happy at around 100 milligrams per deciliter. And this is fasting. So our fasting blood glucose should be around 100. Now, let's say you have your normal blood glucose and then you have a large meal. So there's a spike or a rise in your blood glucose levels. And this is the amount of blood that's circulating or glucose that's circulating in your plasma. So that is going to spike your blood glucose and that is going to trigger an error signal. Okay, let's say it goes up to 120 because of the meal that you just had. Now, the self-correcting mechanism, which is the negative feedback, is going to trigger a response in order to move that glucose into your cells so that it can be utilized to make energy. Otherwise, it's just going to circulate in your blood, and that is not what we want. That is going to throw our set point off indefinitely. So as that mechanism happens, and as blood moves from your plasma, glucose moves from your plasma into your cells, and that decreases your blood glucose levels, that will decrease the error signal. As you can see, the error signal goes down, and then that brings our blood glucose levels back to normal, back to about 100. Okay, so we can think of any number of examples in the body. We can think of many different variables in the body that should be regulated in a very small window. And we can think about how they can be taken away from set point. And then there are various mechanisms to help institute a negative feedback response to bring that back to the desired level. Now, when we think of homeostasis, there are several components that are involved that help to bring about negative feedback, right? There are several players involved. Examples of those are going to be receptors, and receptors are usually detecting any changes to these variables. A good example is that there are receptors on your blood vessels that detect any changes in your blood pressure. There are integrating centers. So integrating centers will usually be in the brain, and they will receive information from the receptors about various stimuli. So the stimulus is the change in the blood pressure. The receptors are going to pick up those changes. They're detecting those changes. Receptors can also be called sensors, by the way. And they're going to send that information up to the integrating centers in your brain. This is usually the medulla oblongata, which is the back of the brain. Okay, the base of the brain, if you will, this region of the brain. The integrating centers are going to take that information and decide, hey, if blood pressure has dropped, I need to tell the heart to increase the rate of firing in order to correct that drop in blood pressure. So the integrating centers will send signals down to effectors. And effectors can be the heart, they can be the blood, the smooth muscle in your blood vessels, they can be the smooth muscle in your GI tract. So the effectors can be different areas of the body, but the heart is going to be the specific response area that will help to correct blood pressure. And then if we think about the signals are the neurologic information that's being sent. So these signals are being sent either to the brain or from the brain, and they're being sent on nerves or neurons, right? And they are sending information, sensory information to the brain, and then motor information to the muscles, whether that be of your heart, your GI, your blood vessels, etc. And then as you can see, the negative feedback response is to rise the blood pressure. The initial stimulus was a drop in blood pressure, and negative feedback is going to change that variable in the opposite direction in order to be a self-correcting mechanism. So that will increase your blood pressure and bring you back to normal. And this loop actually happens every time you go from a lying position to a standing position. So this is all happening without your conscious awareness, which is really fascinating. So every time you raise from a lying position, all of the blood actually begins to settle in your lower extremities. And so what that does is the upper parts of your body, your brain, your upper limbs, your thoracic region, will detect a stimulus that blood pressure has fallen because the blood has pooled to your lower extremities. And so this self-correcting mechanism is triggered immediately, and that brings blood back to all the areas of your body equally, and that corrects the error signal. So if we look at some examples of these different components, receptors, which we said can also be called sensors, their job is to detect the stimulus. Examples of receptors are going to be thermoreceptors that detect change in temperature. Chemoreceptors detect change in chemical balance or chemical makeup, so how much sodium, potassium, or other chemical substances are in the blood or in the oxygen, for example. Chemoreceptors can detect how much oxygen or CO2 is in your oxygen. Baroreceptors detect changes in pressure. So these are the ones that are going to be on your blood vessels to detect how your blood pressure, how high or low that blood pressure is. So thermoreceptors for temperature, chemoreceptors for chemicals, and then baroreceptors for touch or pressure. Integrating centers are going to be orchestrating the correct response. They're usually in the brain, and they're going to take all the information that is coming in and determine what is the best response in order to correct this change and send that out to the appropriate effectors. Signals are going to be the communication that is being sent, usually on neurons. So the input signals are going to be from the receptors up to the integrating centers in the brain. The output signals are going to be from the integrating centers and out to the effector tissues or effector organs in the body. And the signals are usually going to be chemical messengers, so neurotransmitters basically that are going from one neuron to the other that help to transmit these signals by way of these chemical messages. Effectors are going to be responsible for the body's response. Examples of effectors will be muscles or glands, so smooth muscle, striated muscle of your skeletal system, or even cardiac muscle. Those are all examples of effector organs that can pick up the information from the brain and make changes that will help to self-correct the initial stimulus. Okay. Here is a schematic representation of what all of this looks like, right? So just kind of reiterating this in a different way. So here's our stimulus, and then here's our sensor or receptor, which picks up the stimulus. And remember, the stimulus is really just a change in the variable. So if blood pressure drops, that's a stimulus. If blood temperature or body temperature drops, that's a stimulus. So that is picked up and regulated by a sensor and then sent to the integrating centers in the brain. The integrating centers in the brain will send a corrective instruction to the effector organ. So if blood temperature, for example, dropped, then the corrective mechanism is for shivering to occur. And for shivering to occur, your muscles, your skeletal muscles have to get excited and sort of spasmically contract. So those instructions are sent down to your skeletal muscles, which will be the effector organ in that example. And then the response is brought about, and that will turn off the initial stimulus. So this is a negative feedback loop. And then down here, we can see that same example being played out. The initial change detected on sensors, the integrating centers making the best response and sending those instructions to the effector organs, and then the effector organs bringing about the desired response to bring that back to the correct set point value. Okay. And so the mechanism of negative feedback loops is that they're always going to be moving in the opposite direction from the change. They're always going to make the gap between the set point and where we are, they're going to make that gap smaller. They're going to shrink that gap. So it's going to basically bring us back to set point. And they're going to reverse any of the changes that were initially happening to trigger the stimulus. So if I had an increase in blood pH, the change in the negative feedback loop is to decrease my blood pH. So this is a continuous and ongoing process, always making fine adjustments, always making fine changes, and always sensing and detecting. So in order for homeostasis to be effective, there has to be mechanisms that are always sensing and detecting if there are even the slightest change in your blood pH. slightest change in your blood volume, your body temperature, your blood pressure, those are going to be picked up. So the body is very sensitive to any of those changes, and those will all trigger a stimulus in order to generate that negative feedback loop. Okay. Here is another example, yet another example with our body temperature. So the average set point temperature, which is about 37 degrees Celsius, is where we like to be. And so our brain and muscles and sweat glands and so forth are going to be involved in order to maintain that. So let's say we step out and we are in the cold and it gets really cold and our body temperature drops. We're going to start shivering. The muscles of our body will start contracting in order to bring about shivering and generate body heat. That is going to self-correct and bring us back to set point. Let's say the opposite occurs. It's a really hot day, or we're dehydrated, or we're out in the sun, and our body temperature rises. That is going to also trigger a stimulus, which is going to allow our sweat glands and even our skin to generate cooling mechanisms that are going to release sweat, and sweat actually helps with cooling by way of evaporation. So when that water sits on the surface of your skin and that evaporates, that generates a cooling sensation. And so that will help to bring us back to 37 degrees Celsius. Okay, so feedback loops or negative feedback loops can occur in both directions. They're just going to be in the opposite direction of the change.